Chicago, 1892 to 1950.
Well, I suppose I'm going to be the first person maybe not to thank the organizers, but but I will thank MSRI for the invitation to participate and to have a History of Mathematics workshop here at MSRI. It's been a real honor for Jeremy and me to put this together and to have the opportunity to try to integrate history of mathematics with the mathematical activities here at MSRI. I want to talk today about the University of Chicago and its role in what I hope to argue and convince you of, its role in creating a school of algebra during roughly the first 6 decades of its existence. The University of Chicago opened in 1892 as an institution of higher education devoted to undergraduate and graduate education for young men and women, as well as to the production of original research and the training of future researchers. Reflective of changes in higher education, especially during the closing quarter of the 19th century, the new, adequately and privately endowed university sought from its founding a faculty capable of realizing all of those institutional goals. In mathematics, the first faculty, what we might call the members of the first generation of research mathematicians on American shores, consisted of one American, Eliakim Hastings Moore, and 2 Germans, Oskar Bolza and Heinrich Maschke. The American, Eliakim Hastings Moore, had earned a doctoral degree at Yale College for a thesis on n-dimensional geometry in which he had extended some earlier work of William Kingdon Clifford and Arthur Cayley. Moore had then made what was at that time the obligatory trip to Germany. He went first to Göttingen for a summer of language training, and then to Berlin for a year of exposure to the mathematics of people like Karl Weierstrass and Leopold Kronecker. When did he go to Germany? That was in, let me just think. I have to do the math. That would have been, I guess, 1887? I'll double check the date. When the University of Chicago was putting together its faculty, Moore was teaching at nearby Northwestern University and eagerly accepted the call to a professorship and acting headship of Chicago's new Department of Mathematics. Almost immediately on arriving at Chicago, his research interest shifted from geometry to algebra, a move spurred most likely by Chicago's evolving mathematical environment. In the first winter term at Chicago, that was the winter term of 1893, Bolza was teaching a graduate-level course on the theory of permutation groups based on works of Joseph Seurat, Camille Jordan, and especially Eugen Netto. And Maschke continued his research in the theory of finite linear groups. Moreover, the department's mathematical club, which was its weekly series of research-oriented workshops modeled on the German seminar, had a decidedly algebraic focus in the university's first year. In this algebraic atmosphere, and in light of what the emergent American mathematical community would soon recognize as Moore's uncanny ability to capitalize on hot research topics, Moore, too, moved into the theory of finite groups and immediately began proving new results. Perhaps his most notable early result, and the work that might be said to mark the beginning of a tradition in algebra at Chicago, was his contribution to the Mathematical Congress held in Chicago in association with the World's Columbian Exposition in 1893. Entitled A Doubly Infinite System of Simple Groups, Moore's Congress paper reflected the abstract point of view then increasingly characteristic of German mathematics, namely the methodology of identifying and classifying mathematical objects. In Moore's case, the objects were finite simple groups, and he discovered an entirely new class of them. At the time of Moore's discovery, there were 4 known classes of finite simple groups in addition to the cyclic groups of prime order P and the alternating groups AM for m bigger than 4. One of these 4 other groups was PSLM-P, projective special linear groups, and those groups have this order where P and M have a couple of restrictions, and where delta is the GCD of P minus 1 and M. Now, Jordan, in his Traité de substitution of 1870, had done quite a bit of work on this class of finite groups of substitutions over the prime field, ZP, and Moore picked up on that work, focusing on the special case here of M equals 2. One problem Moore encountered was that of a group of order 360 that he had discovered in 1892, as well as a group of order 504 discovered in the spring of 1893 by his countryman Frank Nelson Cole. Now, both of those two groups, the one of order 360 and the one of order 504, failed to fit into any of the 6 known classes of finite simple groups at that time. So Moore soon recognized that these groups fit into a new class of what he termed doubly infinite, or 2-parameter groups, of order p to the n times p to the 2n minus 1 over delta. And he showed that all these new groups, what today would be denoted PSL2 of p to the n, are simple. But before establishing his main result, Moore needed to come to terms with the underlying fields with p to the n elements. This led him to an unexpected field-theoretic theorem, namely, every extant field, f bracket s, in the abstract, is the abstract form of a Galois field, gf p to the n, where s is p to the n. So in his efforts to identify and classify finite simple groups, Moore also characterized finite fields in a new and provocative way. What we might call Moore's structural approach to the algebraic questions raised in his Congress paper became even more pronounced after 1901, when he also embraced the axiomatic point of view that Hilbert had presented in his Grundlagen der Geometrie. An abstract and structural approach came to characterize much of the algebraic work that issued from the University of Chicago over the first half of the 20th century. Now, the first student to be influenced by Moore's new brand, or sort of emerging brand of algebraic ideas, was Leonard Eugene Dixon. Dixon had come to the University of Chicago in 1894 to pursue graduate studies under Moore, and in 1896 had earned one of the University of Chicago's first 2 PhDs in mathematics. Dixon's thesis, called The Analytic Representations of Substitutions on a Prime Power, on a power of a prime number of letters with a discussion of the linear group, long title, followed directly on the work Moore had done in his Congress paper in 1893. Dixon focused structurally on the finite fields gf p to the n, where p is prime and n is an integer, positive integer, the same fields that Moore had worked with in his Congress paper. Dixon considered a polynomial, phi of x, of degree k less than or equal to p to the n, with coefficients in f, and defined an associated mapping, phi, from f into f, which takes c to phi of c. He called this thing a substitution quantic of degree k on p to the n letters, provided it was bijective. So the first part of his dissertation aimed at, and this is a quote from the dissertation, a complete determination of all quantics up to as high a degree as practicable, which are suitable to represent substitutions on p to the n letters. And he obtained a complete result for degrees k less than 7, with partial results for degrees 7 and 11. Well, it's the second part of the thesis that's maybe more interesting to us here. There he took up the general linear group GLMF, where, as in part 1, f is gfp to the n. Jordan had already studied these groups for the finite fields, f being gfp, in his traité, but in the spirit of Moore's move from singly to doubly infinite finite simple groups, Dixon sought to generalize Jordan's structural work to fields with p to the n elements. Dixon thus showed that his GLMF was a group, he determined its order, and he examined its composition series. The latter analysis led him to one of his main results, namely, if z is the center of SLMF, then SLMF mod z is simple, except in 2 cases. Dixon's theorem thus generalized his advisor's approach of 1893 to triply infinite systems of simple groups, here the 3 parameters being m, n, and p. at the same time that it exploited Moore's structural approach to algebraic questions. Moreover, Dixon's analysis also uncovered a previously unknown class of finite simple groups, these being SLMF mod Z for m bigger than or equal to 3 and n bigger than 1. So now we have yet another new set of finite simple groups. So Dixon followed his doctorate, which was in 1896, with a year-long foreign study tour, again, the obligatory move for a mathematician in the United States at this point in time. His foreign study tour took him first to Leipzig, where he worked with Sophus Lie, and then to Paris, where he sat in on lectures of Camille Jordan. Following teaching positions at the University of California, Berkeley, here, and at the University of Texas, Dixon returned to Chicago as an assistant professor in 1900. Following year, an expanded version of his doctoral dissertation appeared as his well-known book, Linear Groups, with an exposition of the Galois field theory under the Teubner imprint, which was a really big deal for an American at that time to have a book in English published by Teubner. Also, in 1901, Dixon saw his first student successfully through to the PhD. In all, Dixon supervised the doctoral work of almost 70 students during his 39-year career at Chicago, and this process began just as E.H. Moore was moving out of algebra and shifting into research of a more foundational nature. In a real sense, the algebraic mantle at Chicago passed in the early years of the 20th century from Moore to his student and now colleague, Dixon. Moreover, the approach, as well as the kinds of mathematical objects that Moore had pursued, continued to characterize the algebraic work coming out of Chicago. The imprint of an emergent Chicago style of algebra can be detected in that first decade of the 20th century, not only in Dixon's work, but also in the work of at least one notable visitor to Chicago during the 1904-1905. Oh, sorry. Yeah, sorry. He didn't mean to turn his back on the audience, but yeah, so Wedderburn visited the University of Chicago in 1904-1905. At this point, he was a mathematician in training. He had won a Carnegie Fellowship and had taken it first to Germany and the universities of Leipzig and Berlin, but then followed that up with a year-long stay in Chicago. Wedderburn's choices of where to take his Carnegie Institution Fellowship are interesting. They suggest that the algebraic research coming out of Chicago by 1904-1905 had grabbed some attention internationally. This Scot mathematician decided it was Chicago that he wanted to go to next. The 1904-1905 academic year was another very active one in Chicago. Moore was heavily involved in his new interest in foundational questions that Leo pointed out to us in his talk yesterday. And he had been working on problems of determining a suitable set of axioms for a group. Dixon had also been seduced by this type of foundational work, focusing on sets of axioms for fields and for linear associative algebras, while he continued his researches on linear groups. Wedderburn came into direct contact with both of these mathematicians, and their approach very much influenced his mathematical choices. By January of 1905, Wedderburn and Dixon were in a friendly but intense competition to answer the question, is every finite division algebra a field? Reminiscent of Moore's characterization of finite fields as Galois fields in his 1893 Chicago Congress paper, the question was at the same time structural and concerned with abstract algebraic objects. Although Dixon's work suggests that he thought the answer to the question was no, Wedderburn had proved the theorem in the affirmative by March of 1905, and in so doing had unwittingly embarked on a career devoted to understanding the structure of linear associative algebras and related algebraic structures. Wedderburn returned to the University of Edinburgh in the summer of 1905 to take up a position as lecturer in mathematics and to continue work toward his doctoral degree. The main piece of research that he submitted for that credential in 1908 was his groundbreaking paper of 1907 on hypercomplex numbers. Wedderburn had completed an early draft of that work while he was in Chicago during the 1904-1905 academic year, and it bore the clear imprint of the emerging Chicago style of algebra. Wedderburn's predecessors, mathematicians like Theodore Morlin, Georg Frobenius, and Élie Cartan, had worked with linear associative algebras over algebraically closed fields of characteristic zero, and their techniques had hinged on properties of the underlying field. Wedderburn, though, took a more general approach, working primarily over arbitrary fields, and developed new, substantially field-independent theorems and techniques. Moreover, he sought the underlying structure of linear associative algebras, how they were put together, so to speak. Exploiting the elegant technique of decomposing his algebras using idempotent elements, Wedderburn proved, among other results, that if A is an algebra over a field F, then, first of all, if A is simple, it can be expressed as the tensor product of a division algebra and a full matrix algebra. Second, if A is semi-simple, then it's the direct sum of simples. And third, the so-called Wedderburn principal theorem, namely, and I apologize, I notice I have a typo here, if n is the maximal nilpotent ideal, or radical of A, then A contains a subalgebra B isomorphic to A mod n, provided F is a field of characteristic zero. So he does need the characteristic zero there in the principal theorem in the 1907 version. He wasn't able to do that for in any arbitrary kind of case then. As he acknowledged in the printed version of his 1907 paper, quote, "The greater part of the paper was read in the mathematical seminar at the University of Chicago early in 1905, and owe much to Professor Moore's helpful criticism." Meanwhile, back in Chicago, Wedderburn's contemporary, Dickson, continued to produce voluminously on the theory both of linear groups and of linear associative algebras. By 1914, he had paused briefly to take stock of what had been the rapid development of the theory of algebras, producing a terse 73-page book called Linear Algebras. There, he aimed to bring together some of the key results in the field, but as one of his biographers noted, it was more than somewhat ironic that Dickson, quote, presented the Cartan theory of linear associative algebras rather than the Wedderburn theory, although he, quote, stated the results of the latter theory in his closing chapter without proofs. So the somewhat messy, although groundbreaking work of Cartan here from the late 1890s concerned itself with the structure of the entire algebra, including the nilpotent part. Wedderburn's theory, or his approach, hinged on factoring out the nilpotent part and concentrating on the better-behaved semi-simple part. Why Dickson made this choice of emphasizing the Cartan theory as opposed to the Wedderburn theory is not quite clear, but he would rectify that mistake a few years later. In the meantime, the 19-teens found Dickson consumed by number theory, and he published his massive 3-volume history of the theory of numbers between 1919 and 1923. In some sense, his interest in algebras and in number theory coalesced in another of his groundbreaking works, the 1923 book on algebras and their arithmetics that came out in a greatly expanded German language edition in 1927. This research not only corrected the mistake Dickson had made in his 1914 track of emphasizing the Cartan theory as opposed to the Wedderburn theory, but also solidified Dickson's own international reputation. Moreover, it reflected a key point of contact between Chicago's algebraic tradition and algebraic work being undertaken in Italy. So this is the first time I think maybe Italy's come up in our workshop so far. In 1921, the Pisa-trained Gaetano Scorza published his gigantic treatise Corpi numerici e algebri in direct response to Dickson's 1914 tract on linear algebras. Scorza recognized that Dickson had made a tactical error in presenting the more old-fashioned work of Cartan in detail rather than what Scorza viewed as the more trend-setting Wedderburn approach. Clearly, anyone who wanted to get into the new theory would need a complete exposition from Wedderburn's and not from Cartan's point of view, and Scorza aimed to provide exactly that in his book. As he explained in his preface, the theory of algebras had developed sufficiently, by 1921, to merit a treatise in which all of its various results were brought together. And although Dickson had published his short tract in 1914, it was so characteristically terse that it was difficult to get from it, in Scorza's words, an adequate idea of the numerous and important results that had been obtained up to the present time. So Scorza sought to pull together, for his primarily Italian audience, since the book, after all, was written in Italian, all the results that could only be found scattered throughout the pages of journals internationally. And he wanted to introduce what had become the standard algebraic terminology into the Italian mathematical vocabulary. So he's really presenting translations of these various technical terms into Italian for the first time. Scorza divided his book into two parts and a substantial appendix. The first part laid out the theory of fields in some 120 pages, taking an axiomatic point of view that drew directly from Dickson's 1903 work that Leo mentioned yesterday on the definition of a field by independent postulates, as well as from Dickson's 1901 book on linear groups. The second and most substantial part of Scorza's book developed the theory of algebras per se in just under 300 pages. But so unlike Dickson's really terse 1914 tract, number one, it wasn't terse. Number two, it presented Wedderburn's version of the theory, setting the stage with an axiomatic treatment of matrices and their properties before launching into an exposition of the Wedderburn structure theory. Finally, the 50-page index appendix, focused on applications of the theory of algebras in an effort to highlight its richness and its importance. So he was really trying to sell the theory of algebras as a new research topic for his Italian contemporaries. Throughout the book, Scorza brought algebraists in Italy into direct contact with the algebraic ideas that had issued from the Chicago mathematical environment. I mean, he's responding directly to Dickson and that work. In so doing, he hoped to unite his Italian contemporaries with a growing group of American algebraists interested in the theory of algebras and its related areas. So to a large extent, that group of Americans issued from Chicago and from the classrooms of the second-generation American Leonard Dickson. As Della Fenster has shown in her extensive studies both of Dickson's mathematics and of his mathematical persona, Dickson was a highly effective, if also highly idiosyncratic, role model for budding mathematicians. He imparted to them his sense not only of what areas merited attention, and that was primarily the theory of algebras, and later the related theories of rings and division rings, but also of the kinds of questions that should be asked. And those were primarily structural questions aimed at understanding the object's internal organization and construction. Moreover, Dickson presented to his students, through his own personal example, an image of the driven researcher guided by the highest possible standards. Among Dickson's students in algebra, Olive Hazlitt earned her doctorate in 1915 for a classification of all, not necessarily associative, nilpotent algebras with 4 or fewer basis elements over C that drew directly from Wedderburn's 1907 work. Hazlitt, who eventually secured a position at the University of Illinois in 1925, represented an interesting feature of Dickson's training of future researchers, namely the encouragement of women in research-level mathematics. In fact, 18 of his almost 70 PhD students were women, making Dickson personally responsible for slightly more than 8% of all women PhDs in mathematics in the U.S. between 1900 and 1940. Pretty interesting statistic. Although Hazlitt didn't find herself in a position conducive to the training of future researchers at Illinois in the 1920s, she did manage to continue her own research agenda while she was on the faculty there, lecturing on her new results on the arithmetic of a general associative algebra at the International Congress of Mathematicians in Toronto in 1924, and publishing some 17 papers despite a career plagued by mental breakdowns. Another Dickson student, C.C. McDuffie, finished his PhD in 1921 and immediately went to Princeton to a Wedderburn. By 1924, McDuffie had moved to the Ohio State University, and 9 years later had authored the widely read textbook, The Theory of Matrices, again drawing directly from Wedderburn's development of matrix theory. But the most famous third generation student directed by Dickson was Adrian Albert. He earned his doctorate at Chicago in 1928 at the age of 23 for a dissertation in which he proved, among other results, that every central division algebra of dimension 16 over its base field is not cyclic, but is always a cross product. This work drew fundamentally from two papers. One, a 1906 paper of Dickson's in which he defined the concept of a cyclic algebra, and the other, the 1907 paper of Wedderburn on hypercomplex numbers. So still Dickson, Wedderburn, they are the two main inspirations for this work. This intellectual lineage, as well as the fact that Albert immediately followed his doctoral work with a year-long stay in Princeton, attracted, in Jacobson's words, by that great master of associative algebra theory, Wedderburn, further exemplifies the mathematical and intellectual continuity of Chicago's program in algebra. Now, the question that Albert examined in his dissertation was timely. In the structure theory he presented in his 1907 paper, Wedderburn had effectively shown that the study of finite dimensional semisimple algebras reduces to the problem of figuring out the division algebras. So the search for division algebras, and in general the classification of them, became a focal point of the post-Wedderburn theory of algebras. As early as 1905, in his competition with Wedderburn over the finite division algebra theorem, Dickson had been interested in division algebras, and this interest only intensified in light of Wedderburn's revolutionary structural results from 1907. In 1906, Dickson had defined a new class of algebras, so-called cyclic algebras, which have dimension n squared over the base field. These contain a maximal subfield that's cyclic over the base field. That is, the maximal subfield is a Galois field with cyclic Galois group of order n. Moreover, Dickson noted that the class of cyclic algebras contained division algebras. In 1914, Wedderburn established a critical sufficient condition for a cyclic algebra to be a division algebra. And by 1921, he had extended that work to central division algebras. That is, division algebras with center equal to the base field. Wedderburn showed that every central division algebra dimension 9 over the base field is cyclic, and proved that Dickson's cyclic algebras were actually special cases of what would come to be called abelian cross products. Then Dickson, in 1926, showed that abelian cross products could be generalized even further to cross products based on any, that is, not necessarily abelian, Galois field extension, and in doing that, generated yet another new class of division algebras. So Albert's main thesis result extended Wedderburn's 1921 theorem to the next case, dimension 16, and demonstrated that a central division algebra can be a cross product without being cyclic. So one thing you see from this transparency is just this dynamic that's bouncing back and forth between these members, all of whom either came out of Chicago or worked at Chicago and were inspired by the Chicago atmosphere, namely that being Wedderburn in this case. And it's just year after year, one bouncing off the other. It's interesting to note that Albert's thesis reflects the existence of yet another algebra-theoretic intersection between American and Italian researchers. In his work, Albert called attention to a 1923 paper of Francesco Cecchioni, published in the Rendiconti del Circolo Matematico di Palermo, in which Cecchioni independently hit upon the class of abelian cross-product algebras, drawing, as Albert had, from the work of Dickson and Wedderburn. Same exact inspiration, independent discovery. Just like Dickson's student Albert, one of Wedderburn's students, Nathan Jacobson, also became caught up in the quest to understand cyclic and cross-product algebras. In 1909, Wedderburn had left his native Scotland to spend the rest of his academic career at Princeton, where he continued to work on the theory of algebras and on matrix theory. Circumstances, though, resulted in the fact that he only had 3 doctoral students, but one of those, Jacobson, not only continued in Wedderburn's mathematical footsteps, but also completed, in a very real sense, the structure theory that Wedderburn had been so instrumental in establishing. Jacobson earned his PhD in 1934, 6 years after Albert, for a thesis on non-commutative polynomials and cyclic algebras. Wedderburn had suggested the topic to him, But Wedderburn was motivated by the following question. Do there exist non-cross-product central division algebras? So that was the question he really put to Jacobson. Jacobson couldn't answer that question, but he did come up with some new results on cyclic algebras that constituted his dissertation. It was also during the course of his doctoral studies at Princeton that Jacobson became aware of Wedderburn's 1924 paper on algebras which do not possess a finite basis. A paper, according to Jacobson, that was, quote, one of those that inspired my later work on the structure theory of rings. That later work was also informed generally by Emmy Noether's ring-theoretic researches of the 1920s and 30s, and more particularly by Emil Artin's extension in 1927 of Wedderburn's structure theory to ring-satisfying descending chain condition for right ideals. In a series of 6 papers in 1945, Jacobson succeeded in taking this further by laying the groundwork for a structure theory of rings without finiteness condition. So remember that in his 1907 paper, Wedderburn always worked with algebras that were finite dimensional over their base field. In particular, Jacobson defined what came to be called the Jacobson radical of a ring, a structure in an arbitrary ring in some sense analogous to the maximal nilpotent ideal in a finite dimensional algebra. Yetzirstein, another ring theorist fundamentally influenced by Wedderburn's research and his approach to the theory of algebras, described the import of the Jacobson radical with characteristic clarity. In order to study a general ring, Herstein wrote, we want to slice out of the ring a certain piece, the so-called radical, in such a way that we don't slice out too much so that the piece being cut away is capable of description, yet at the same time we don't want to cut out too little so that the object resulting after the excision is also capable of description. Jacobson provided a complete exposition of the structure theory of rings in 1956 in his highly influential book called Structure of Rings. Jacobson ultimately transplanted to Yale University the brand of algebraic inquiry that his advisor Wedderburn had imbued at Chicago, although, as I mentioned, in a form enhanced further by the ideas of Emmy Noether. At Yale, he trained such fourth-generation students as Charlie Curtis and George Seligman. These and other students worked on the theories of various kinds of algebras, both associative and non-associative, and in ring theory. As for Albert, he followed his first postdoctoral year with Wedderburn in Princeton by 2 years as an instructor at Columbia. He then returned to a position at Chicago in 1931 and remained there for the rest of his life. His work continued to center on the theory of algebras. In 1931, he came within a hair's breadth of winning the biggest prize in the field, namely the determination of the complete classification of all rational division algebras. Remember, that was basically what the classification had boiled down to thanks to Wedderburn's principal theorem, or rather, thanks to Wedderburn's 1907 paper. Albert's work continued to center on the theory of algebras, as I said. When he just missed this classification, he missed it at the hands of Richard Brouwer, Helmut Hasse, and Emmy Noether. So it's not like he lost out to any shabby mathematicians, but he was very close, and they ended up writing a joint paper in which they tried to sort out just who did what when. Now, Albert was stung by this incident, but he went on to do quite a lot of work, in particular to publish his influential treatise, Structure of Algebras, in 1939, before his interests, like those of his contemporary Jacobson, moved from associative to non-associative algebras. Still, Albert remained in some sense obsessed for the rest of his career with cross-product algebras, these algebras he had studied in his doctoral work. He was convinced that, in fact, every central division algebra is a cross-product algebra. Ultimately, he wasn't able to prove that, and in 1972, just a few months before Albert died, Shimshon Amitzur found a counterexample. So Albert's intuition on that point was wrong. Like Jacobson at Yale, Albert passed on, during a 40-year career at Chicago, his brand of algebra to a number of students who perpetuated and developed it. Among them, Daniel Zielinski earned his PhD in 1946 and went on to teach during a long career at Northwestern. Richard Block finished his doctoral work in 1956 before taking a position at Caltech. So what we see from this list, if we could go on with different examples, we have these students spread from coast to coast. So these and other fourth-generation students from the 40s and 50s continued their research, primarily in ring theory and in the theory of non-associative algebras, wrote textbooks, and trained their own students well into the 1990s. So, where are we? Yeah. Yeah. He's not a physicist, no. No. This is Richard Block, the algebraist. Yeah. And he didn't stay, I didn't look up how long he stayed at Caltech, but he moved on to Riverside eventually. Okay, so with this overview of Chicago-connected algebraic results, we now have the question being begged, what constitutes a mathematical school, and was there something that could properly be called a Chicago School of Algebra? Mathematicians tend to use the term school loosely. Often one hears the set of PhD students of mathematician X who happens to be located at institution Y referred to as X's school or the Y school. But exactly what analytic value does this informal notion of school have in trying to assess meaningfully the real intellectual connections between mathematicians or the complex development of mathematical theories? Well, historians of science also use the word school, but for them, a school is almost exclusively something associated with the laboratory sciences, so mathematics falls completely out of their purview. Still, historians of science have tried to provide a definition of school as an analytic construct for evaluating and understanding the past. So what I want to do now is just pause to consider some of the definitions that historians of science have given and how we might tweak those to make them meaningful in the mathematical context. And then we'll return to the still open question of whether and to what extent there was a Chicago School of Algebra. In what's become a classic study in the history of science, the British historian of science J.B. Morrell considered the notion of research schools in his 1972 analysis of the 19th century chemists Justus Liebig and Thomas Thomson. In Morrell's words, the concept of a research school, quote, centered on laboratories in which ambitious disciples devotedly served an apprenticeship and afterwards produced knowledge under the aegis of a revered master of research. This conception was thus clearly shaped by the image of the crowded laboratory in which students and professors worked shoulder to shoulder on some experiment or program of experiments conceived of and orchestrated by the seemingly all-knowing director. Morrell then proceeded to lay out 7 criteria for a research school. So here are Morrell's criteria. First of all, you have to have a leader. And for Morrell, this leader is some charismatic figure who has some all-knowing sense of where he, and it is he in the 19th century in Morrell's examples of chemistry, where he wants this research to go. You also have to have manpower, or students, people who are coming there who are going to be doing the grunt work in the laboratory. That's how this laboratory context plays out. You also, according to Morrell, have to have an area of inquiry with relatively simple experimental techniques that can be applied by both brilliant and just ordinary students to solve significant problems. Okay, so things that can just kind of be tidied up by students in your laboratory. So the tidying uppers and the brilliant students side by side. You also need publications because that's how the school is going to communicate both with the outside world and even with other members of the school. The leader needs institutional power to allow for the realization of his research goals. Like I said, he's supposed to be charismatic, and he needs institutional support to assure the stability of the laboratory. So all of us in mathematics certainly have heard these arguments by the laboratory scientists today, why they argue for so much money than we ever get from NSF, for example. Anyway, so this definition of a research school is clearly geared towards this mental image of how things play out in a laboratory. and it doesn't particularly apply well to the case of mathematics in all of its different points. Another historian of science, Gerald Geeson, drew from Morell's work at the same time that he was guided by his own research on the 19th century Cambridge physiologist Michael Foster in coming up with another definition of research school. In his 1981 article called Scientific Change, Emerging Specialties and Research Schools, Geeson defined a research school as, quote, a small group of mature scientists pursuing a reasonably coherent program of research side by side with advanced students in the same institutional context and engaging in direct, continuous social and intellectual interaction. For Geeson, then, even perhaps more so than for Morell, the close physical proximity and interaction of individuals was critical to the existence of a research school. He did offer at least one caveat to his conception of a research school as a unit of historical analysis, though. He noted that, quote, it might be necessary to acknowledge the existence of spatially dispersed research schools, or at least to recognize and take account of the extent to which the members of a research school may extend its geographic scope by moving elsewhere. So Geeson was willing to sort of open the door of the laboratory and let these people leave that one enclosed space. So the precise definition aside, Geeson argued that as an analytic tool in the history of science, the notion of a research school has the potential to, quote, enrich our understanding of emerging specialties, and to, quote, refine our efforts to specify the conditions under which innovative science is most likely to be done. So while historians of science have continued to debate and refine the concept of a research school, very little, if any, of this discussion and debate has focused on examples presented by mathematics. So let's consider then what an appropriate definition for a mathematical research school might look like. Okay, so first of all, although mathematics certainly has an important sociological component, it lends itself much more naturally and easily than do the experimental sciences to the individual investigator or to small groups of one or two or three, well, small groups, 2 or 3 investigators in collaboration. It's not done in the context of the expensive sort of infrastructure of a laboratory. It doesn't require the kind of close physical proximity and interaction of individuals necessarily that's so central to Geeson's definition. It's linked in some sense more by ideas than by geography. Still, mathematics does share certain characteristics with the laboratory sciences. It's learned by a kind of apprenticeship. The graduate student working in association with an advisor is generally guided into a mathematical area and toward a particular problem or set of problems. But unlike the laboratory context, the problem or set of problems may not have any direct bearing on some larger or immediate research agenda of the advisor. The idea in mathematics is to sort of get your student off into something that they can then make their own career out of. In mathematics, perhaps more so than the experimental sciences, at least as Morell characterized them, the student is less a blind apprentice and more an evolving independent researcher. The student most often leaves the advisor's institutional context to pursue research elsewhere, and in so doing transplants mathematical ideas elsewhere. Finally, a stronger similarity between mathematics and the experimental sciences centers on the means of communication. Mathematicians, like experimentalists, communicate with each other informally, of course, but also formally through publications. And publications establish not only priority, but also reputation. Journals and books serve as the record of the ever-evolving body of mathematical knowledge. So, if we put all those things together, they suggest what's at least a first approximation of what might be a meaningful definition of a mathematical research school. First, a mathematical research school initially requires a leader who actively pursues research in some particular area of mathematics. That leader might be charismatic, like Morell's laboratory directors, but it's not a necessary condition, I don't think, for a leader of a mathematical research school. Maybe in mathematics it's the ideas that need to be charismatic more than the person who's actually promoting them. Second, that leader advocates a fundamental idea or approach to some set of inherently related research interests, or research interests that become related by virtue of the idea or approach. Third, the leader trains students, and in doing so, imbues them with a sense of the validity and fruitfulness of the approach. Those students then go forth and pursue research according to that approach, so that the ideas and approach naturally extend beyond the leader's original institutional setting. In this process, the original leader might pass from the scene, but is replaced by another like-minded leader or leaders who train students appreciative of and actively engaged in research informed by the approach. Fourth, publication of the research not only represents recognition of the research done, but also comes to reflect the external validation of that approach. This external validation might result in the extension of the ideas and approach by other researchers, both nationally and internationally. According to this definition, the mathematical research school is thus a vehicle for the formation of new research specialties, and hence is an analytic tool for understanding at least one way that mathematics changes and develops over time. So, finally, the question that was in the title of the talk. In light of this definition, what about the case of Chicago and algebra? Well, there was a recognized leader, E.H. Moore, an energetic, although not particularly charismatic research mathematician who was interested in the 1890s in algebraic ideas stemming from the theory of finite simple groups, and who approached his research from a structural and, after 1901, axiomatic point of view. Moore supervised the doctoral research of Leonard Dixon, who took up not only Moore's general area of research, but also his sense of what questions to ask. Moore and Dixon both fundamentally influenced the mathematical approach and the area of interest of the visiting Scott mathematician, Joseph Wedderburn. Wedderburn at Princeton and Dixon at Chicago continued to pursue research questions about the structure of algebras and later of related objects like division algebras, while Moore moved out of algebra and into function theory. Although neither Dixon nor Wedderburn was particularly charismatic, both did research, which they published in journals like the Annals of Mathematics, the Transactions of the AMS, Crella, the London Journal, the Journal of the London Math Society, and others that became widely recognized as fundamental and even groundbreaking. As evidence of this recognition and interest, the Italian mathematicians Gaetano Scorza and Francesco Cecchioni self-consciously engaged with, codified, and extended the American work. Moreover, Dixon's work in particular reached the German context directly through the German translation of his book, Algebras and Their Arithmetics, and both Dixon and Wedderburn and others published some of their research directly in German journals. In a similar spirit, students were attracted to the classrooms of Wedderburn and Dixon and were brought to the research level in the theory of algebras, eventually both associative and non-associative, and in the theory of division algebras and in ring theory. These students and their mentors were not blinded to developments going on elsewhere, though. They freely incorporated into their approach the latest ideas of mathematicians like Emmy Noether and Emil Artin, and passed that evolving approach on to their students who dispersed throughout the country. The result was new and recognized research specializations in ring theory and the theory of non-associative algebras, characterized by the quest for the object's underlying structure. So here I haven't ventured beyond the fourth generation of American students and have only touched on the issue of geographical extent. But 4 or 5 things actually do seem clear. I hope they seem clear anyway. First, the definitions of research school that you can find in the literature in the history of science are just inadequate for mathematics. Second, it should be possible to define the concept in the mathematical context in such a way to provide a useful analytic tool for understanding better at least one type of historical development within mathematics, namely the formation of subdisciplines. Third, a natural but perhaps not necessary component of that definition should be the idea of geographical dispersion of mathematical ideas. Fourth, further research in the history of especially 20th century mathematics might benefit and be meaningfully shaped by the analytical tool of a suitable definition of research school. And fifth, at least by the tentative definition I gave you here, I think there was a Chicago School of Algebra between 1892 and 1950. Thank you.
Thanks, Karen. Do you have any questions? Leah.
Well, thank you for the very interesting and suggestive talk, and raises many questions in both sides. First in the story itself, and then the meta story or history that you present. So I'll try to raise two questions, one here and the other one. I think it's remarkable that there is no apparent contact between the story that we heard the previous few days on research of factorization, rings, etc. in Germany, and what happens in the United States. Or there is little contact until Jacobson, as you presented the story. I'll tell you.
Okay, you finish and then I'll comment.
Exactly. So I put it simplistically, and then you come. And I wonder if you use all the time the word structural, which I also mentioned yesterday, and I wonder if there is not a difference in the way this work can be applied to what was done in America and what was done in Germany. Again, simplistically put, but schematically we can follow this line. In the sense that in Germany, I think if I take the example of Steinitz that I mentioned yesterday, you have a certain entity and you look for the extensions and substructures or whatever and the relationship. Whereas in the American case, it is more to see certain elements, idempotence, etc., and how they interact. But then in Jacobson, I think there is a merger of these two approaches, in the sense that now instead of looking at nilpotent elements, I look at nilpotent ideals or things like that. So that's the question. Is there a difference in the way the word or the structural conception of what's being done is different in both cases? This is the first.
Okay, so
the second one relates to the second part. I wonder why it is so important to define what a school is and then to see if it fits. I think that what you did in the first part is define what a school is. That's a school. The Chicago tradition or whatever. I understand very well after your talk what it is. After the first part of your talk, what is a school. After the second, we may be in debate. For example, you speak about charisma, things like that. I don't know. I have no idea about Dixon's personality. But if he had 70 students, well, that's kind of charisma, I would say. Silent charisma, I don't know.
Non-negative charisma.
Whatever. Important charisma, I don't know. But the fact is that you have shown something that perhaps has no parallel in other cases. And if people want to call that school or tradition, whatever, I don't care so much. The case is interesting. It has a coherence, etc. And I don't see very much. There are many cases that if we have revolutions in mathematics, if we have school in mathematics, etc. And these debates are always. I don't see they are very useful, except for the case of sharpening your own discussion and see what you have done while describing it. But if it's of no use in another case, it's not important. I think it was of great use in your case, and that's fine.
Okay, so let me answer your first question first, or at least try to address it, and then say something about your second point. So yeah, I think there is something fundamentally different between the American developments here and the German developments that were going on parallel, and it goes back to the point you made in your talk yesterday about this emphasis in the United States beginning with E.H. Moore in 1901 on this postulational method. And that gives them, that sort of takes them, the Americans that is, along a certain path, which is kind of parallel but different in sort of spirit from what was going on in the German case, and focuses them more on sort of the finer, what's the best way to put it, sort of, like you said, the elements inside rather than the broader structures of these things initially. So I think that emphasis perhaps on the postulational side of things is one of the differences between the two sides. Now, as for your second comment, okay, so let me say a couple of things. First of all, thank you. I mean, I'm glad that you agree that the example that I gave describes a research school. In the second part, what I then hoped to do was to sort of take the components of that particular example and see what sort of shook out and what was fundamental, comparing that or sort of pitting that against the literature that's in the history of science. Okay, now, does this model that falls out of the example of the Chicago School of Algebra, does it have legs? Can we apply it in other cases? Well, my answer to that is, I don't know, but I'd like to see to what extent this kind of, the kind of school formation that generates the tentative definition that I gave, to what extent that is the way mathematics develops. Can we find other cases? So that was what I was calling for in my fourth point. Other studies, and maybe the results of those studies of other subdisciplines in 20th century mathematics would say, Parshall, you're all wet. Obviously, that's not the right definition, and all mathematics doesn't do that way. I'm not claiming that it does. I'm just saying that in this case, that kind of a model seems to fit, and maybe that kind of a model could help us organize our work as historians in looking at other examples in other subdisciplines. So that's my defense of the second part.
Okay, so I saw Eduardo, Ed, Jeremy. We'll start with Eduardo and see how far we get.
I found your classification most interesting, really. And I have a comment that is that in my own experience as a student, there is a very important element that is some implicit knowledge that is transmitted.
Mm-hmm.
One works on a field, gets to the school where the leader is, and then you discover that there are lots and lots of things that are not in the papers, but that people exchange.
Mm-hmm.
And that is an explosion in your understanding of the field. At least this is the experience I have, and I have recovered also received from people who later in my life have been in touch with me. It's things that are not written, but that everybody in the group knows. You see, that's, I think, a very important element.
Mm-hmm.
For the rest, I found it absurd. The other really question, not comment, that I wanted to ask is concerns really Scorza and the Chicago group. I know the example of the Spanish mathematicians. They were late into going into abstract algebra, but they learned abstract algebra through Scorza. However, once they learned Scorza, they went to Germany, not to Chicago.
Mm.
So I would like to know more of this pivotal effect. It may well be that Scorza really reviewed the Chicago people, and that for the Spaniards it was easier because it's a shorter distance to go to Germany. But to what extent Scorza is really a reviewer of the Chicago school?
Well, just based on what he says throughout the book, that's the tradition that he's presenting. That's the literature that he's drawing from. So, I mean, I think it's fair to say that he is, to a large extent, reviewing what I called here the Chicago school. But then I don't know. I mean, maybe as you say, for the Spanish, it's just was more practical to go to Germany. I mean, it certainly was also a good place to go. But yeah, I'm not sure about the motivations of the Spanish.
I'd like to suggest a modification to your first approximation.
Okay.
To suggest a tremendous importance to the methodology and to the personality, and it's perhaps somewhat in the line of what Eduardo was saying, that what creates a school is some kind of an approach, of a mindset, a method, and I think that's central, and I think that your first approximation overemphasizes the subject matter. It's more the technique than the subject.
Well, that's what I was trying to get at least in point 2 there, the existence of an idea or an approach. And in that word approach, I mean that really as broadly as possible. It's sort of it's kind of like what Eduardo was talking about, the implicit knowledge that one gets, and I sort of had that embedded in that word approach, but it's certainly something I could elaborate on and nail it down a little bit better. But that's what I meant by approach, those more what's the word I